So, buddy, this is Mankind in Training, and I am your host, Joshua Parr. I have a presentation for you this morning. It's going to be a little bit of mathematics, some things that I've been doing, and going to do a little bit of a presentation of some of the things that you can do with Sympy. It's just an incredible program. So I'm going to get to it. There will be coming up the C++ example. I'm going to go right to the C++ website and just run through their tutorial because it's better than anything I could really write up. It's quite detailed. It's a good way to go about things. So what I am doing here, I whipped up the old Jupyter notebook and I have imported NumPy as NP, SciPy as SP, SymPy as SMP, and from SymPy I'm importing everything, star, and import matplotlib.pyplot as PLT. And I then started creating a whole bunch of SMP symbols. You do it just like that with commas in between all of your symbols. Like this right here is H sub n, and that's how you would write that. And then in the SMP symbols, within the parentheses, you get rid of the commas and just have them space delineated. I don't know if I used that word right, just oh. All right. I created a bunch of those, and then I created some variables, fast Fourier transform variables. And down here, we got a variable that it's a function that I'm going to call let's see here. Let's just call that ds not for now. Now, I'm gonna go over some of this with you real quick, what I'm gonna be doing here. So right here we have sigma sub s, and that is representing currently in the example that I'm about to show you that this is the spatial area and this is the dimensions times the number of dimensions that you're working with to make it flexible. So when you see these things, that is what they're denoting. Iota is, when you see iota, that is going to be a complex coordinate vector space for the complex coordinates. In this case, I'm using alpha, beta, and gamma as complex coordinates subject to x, y, and z in the real plane. Kappa, when you see kappa, kappa is denoting the real vector space for the actual Cartesian and XYZ coordinates. When you see X, Y, and Z, those are our Cartesian coordinates, our real actual coordinates for the system that we're tracking and or any energy system from little to big. We're going to be representing that with X, Y, Z Cartesian coordinates, and then it will have its complementary complex coordinates in that vector space, and that will be alpha, beta, and gamma. those are our complex coordinates. And I'm using phi differently than you're used to seeing phi. Phi is going to be and so this is the virtual coordinate system in the complex vector space. And this is the real coordinate system in the actual wave function. I know I'm kind of doing that a little backwards from how it usually is represented because phi is usually connected to the real things. In my case, I'm backwardsing that and saying that psi, the wave function, is the only thing that is real, and phi is the virtual vector space. And then you're going to have the following. When you see that is going to be the target space that we're tracking position over time. So these are the setups that you're going to be seeing. Sometimes there'll be a prime, b prime, or x prime and y prime. Just I want you to keep track of what I'm doing here. I might as well just leave them up there. Meh. Anyway, we'll get on to it. So firstly, I want to show you. We're going to take the constant times sigma x times sigma y times. Now, sigma x and sigma y are representing the weighted space alternate. We're nestled within dimensions, and these are affect. It also can be represented by delta x and delta y when you're measuring difference when the weight is taking up the space. There's an object with an FMA type mass that is just an energy of some kind, an energy system, and it can be represented with delta x. So we got something like this going on here. Yeah, it doesn't care. We got something like this going on here. Now we're adding in iota times d dx dx respect to time dx squared d u times dt squared And these are derivatives that I'm taking. Derivatives for x, derivatives for x with respect to time, and then derivatives for x and y squared with even time squared. And then u is the u cross s, and s is, if you remember, our dimensional quality. Where am I at? I need lambda rho, lambda function, rho, plus now we have the E states, E naught plus E1 plus E sub 2 plus E, yes, plus E sub n times E naught times E sub I divided by beta mu mu u, and then it is minus psi n minus x times alpha x divided by n plus y times beta y times gamma minus L root of, what did I make that? What did I say that was? I made it V1, and that's divided by pi times r squared. Whoops. There we go. Okay, so now what we have here is my initial thing I started out with, the constant, and now it's taking the derivative iota plus with respect to x and delta y. And then we have E naught, big E naught, which is the collective energy eigenstate, its initial basis state. And that we're multiplying that by the time variable. And then we have the collective little e naught, little e1, little e sub 2, plus little e sub n. And that is the collection of energy eigenstates as we progress over the time variable. And then now I'm adding in gamma, big gamma, the collective z coordinate of the virtual particulate space. And then we're taking that minus alpha x times x divided by n plus beta y times y plus n plus our lambda rho function, dt squared dx dy squared all over du. I wrote it completely differently. The computer will write you something mathematically equivalent, but it will rearrange it as it feels necessary. So this looks weird from how you'd usually take derivatives, but it knows what it's doing. When you end up doing it how it has it arranged, it actually seems to work out better. So these trees have a way of solving these things in a way that a human never could. Minus the square root of my V1 variable, which is my vector space coordinates, the real vector space coordinate collective. So once you add up v0 through as it approaches v1, you're going to multiply that by LR squared divided by pi minus xi plus the derivative x with respect to time minus IPU divided by beta mu nu. So, oh, isn't that nifty? We're going to save this as my energy basis state, not, whoa. And then now we're going to create a state that is on. We're going to create a moving state. So what I have to do, all right. That is uh, what do here? Ah! Whoa. All right. That's the whole shebang there, actually. Now this is the on state. It's a little bit more complicated, especially because we have a whole series of products that you have to come up with, but and the connections do become quite ridiculous after a while. So what I'm going to do for you is explain what's going on here a little bit. So my omega is my angular frequency of the particulate energy collection h of x plus the product of all of my states. We have the virtual state, the target state, the actual psi wave function and its Cartesian coordinates, its counterparts. And what we're doing is a summation of x as it approaches the max of what we're gonna cap this one off probably at sigma big X. So as X approaches sigma big X, little sigma big X. So plus C divided by Xn plus the function X T theta divided by tau of N, what N being tau is the collective time variance of everything. So N being the total number of time that you're trying to measure anything over. Minus the difference X and Y. Sigma X and Y, though, are both on the top over the derivative X. But the derivative iota with respect to X is being concatenated here with all of this and the multiplication of the constant, the universal constant. So E naught times the time variant and our energy collection, like I said before. And then here we run into, so this all looks pretty familiar. This was just the function that we just had in the energy basis state 0. Now here's a little bit of something new. We have they rolled our lambda rho function over into this other side that's also being multiplied with this. So we have the lambda rho function times beta mu nu, and beta mu nu is the average representation of the beta state. So alpha, beta, and gamma all have a collection of like potential energy. And the collective beta state and the collective alpha state and the collective gamma state are all multiplied together, and they have an average. They have the most probable virtual positions in a distribution. And beta mu nu is the complete collection of that distribution of alpha, beta, and gamma. It's ABC, the virtual AB, the XYZ, ABC. It's the virtual version of that collective distribution, all multiplied together. So you should think of beta mu nu as a whole collective entity. It's all one thing. And then it plus our phi sub sigma, and our sigma sub x. So like I was explaining in the beginning, our phi sigma state is representing the entire virtual space, sigma, big sigma, the whole collective virtual dynamic space, and the dynamic space as x is related to and is, so as something takes up a space, there's the layers that we're nested in. So as something massive takes up space at all, it's pushing on the dimensions that we're nestled within, and that creates affect. And so that's what I'm representing here with sigma x. Plus u naught, our unknown position, base state for the virtual particles, and v naught, the known the known distribution of the virtual particles in an on state, minus big xi. So xi is like phi and psi are collective wave functions, but this one is the target wave function. And then we're adding the derivative x plus the derivatives a, q, and t with respect to b, plus the E naught state, plus the function x as it relates to v naught over u1, the virtual base state over the unknown on state, plus pu squared times t made complex, logarithmically complex, plus x sub f, plus the ixy wixy, just kidding, xi wi, x sub I is the making complex of our x variable, and v and w is being used to represent the tensor the tensor bundle as it relates to the vector x in the complex vector space in iota, all over the Hamiltonian operator multiplied by the number of dimensions that you're trying to work with, or say that there are, or say that there could be, or you give the Hamiltonian operator the constraint in this situation. So that's the entirety of what I'm going to name the EN basis state 1. Now what I'm going to do is I'm going to take the derivative of the energy basis state naught times the energy basis state 1 divided by ds naught. And then I want to take that with respect to x. Now this got a little unruly. It's a little big. So were the basis states. It's hard to explain things in terms of I'm basically trying to explain what's going on, and it's difficult, hard to do. So what this created when I'm taking the first differential with respect to x, I got gamma and the alpha sub x, which is our relatable value for alpha, and x as they're paired, and then our angular frequency over the function x, plus now we're doing a giant product again, product of all the states. Now I'm going to do it with respect to time. I should do it twice, actually. Well, before I do time, I'm going to do that. Yeah, I'm going to do that. There we go. So the second differential with respect to x, however, is way nicer looking. Ah. So we got -2, the full gamma set squared times a sub x squared over n squared. It's beautiful, the second differential with respect to x. Cleaned it up quite a bit. And then we'll be able to integrate the exact statement here in a moment. What I'm going to do now is take it with time. With time. There we go. There's with time. Look at that. Isn't that just beautiful? and it understands that it has to relate my energy states at the beginning out of the rest of the equation when I'm talking about differentiating with respect to time. It's beautiful. It's a beautiful thing. So let me do this. Let me do it twice. Look at that. That's the only thing that's left is the energy. How about that, mother lover? Lets me know I'm on the right track. So all that's left is the energy over time. You take away, you use all the fluff, but then you take it all away after you differentiate for time. I can use the fluff to calculate, and I can get rid of it. Beautiful thing. So what I'm gonna do now, this might slow us up a bit. It's difficult. It may freeze outright. May put a stop to our presentation right here. Because it does. It's difficult sometimes. It won't do it. So we don't have to sit here awkwardly forever. What I'm gonna do here is I went to the top right here and I changed it from a code cell to a markdown cell. Now this is how you write pretty math. I'm gonna teach you how to write pretty math. So we have the photo. How did it change the code again? I literally just changed it. Okay, so we have the following. If I want to represent this statement right here above, I would say it is ah dt square minus 2 a big E a sub not square. Big E sub not square. Collective energy state, basis state, collective energy eigen states here, E naught plus E1 plus E plus En e to the N plus, no plus, square, just square. That is all. This is statement. Run. Whoops. I do that wrong. Haha, the funny. Isn't that funny? I do wrong. Oh no. Oh no. Isn't that funny? I do wrong. Haha. Oh. Oh, isn't that funny? I still do wrong. Haha. Slash frac. Ah! Why is it doing that? How about that? There you go. That's how you write this right here in Markdown. And I'm going to do it again here. I'm going to show you. So you have to have $signs at the start and beginning. And if you want to have Greek letters, you want to there we are. Integral, derivative, the integral. There was a summation just before that. Ooh, I don't know how to write product. So I'll just do that. See if that works. Yeah. Beautiful. That's how you write some math out. If you want sub, yeah. I could have other characters here too. You'll keep them where they need to be. Use the caret operator for any squaring. Cube that one. Oh, yeah. Don't forget your backslash, people. You won't write it. And there we are. I need to probably get done. I got work. Got work we have to go do. Sorry. Thank you for listening and watching. If you enjoyed, like and subscribe. C++ deep dive. I am doing that. I really am. That's the next video. Thank you.